And it's my very great pleasure to welcome as our speaker today Vincenzo De Risi from CNRS, and he will be talking on the genesis of relationism, Leibniz's early theory of space, and Newton's Scholium. Thank you, Vincenzo.
Thank you very much. Thank you very much, Adrian. Thank you very much to all other organizer. I'm very, very happy to be here. So thank you, and thank you to Niccolo for organizing this session. So I mean, I will give a talk in two parts, and the first will address what Adrian asked about big questions in history of mathematics, and the second one will be on what archives can do to answer this kind of questions, and this will revolve around Leibniz. For I think in fact that he played a prominent role, even if it is not yet well recognized, in the history of geometry. And role is not recognized, in fact, just because Leibniz papers on geometry were almost all unpublished, and they are kept in the Leibniz archive in Hanover. So my important question, I mean, the question in the history of geometry that I am following since many years now, is what made geometry the science of space. That is, how was geometry conceived as a science of space? I mean, it is something that in modern mathematics is often said, at least since a couple of centuries. When we ask what is geometry about, we often answer something like geometry is about space and spatial structures. It's about let's say Euclidean spaces or non-Euclidean space or projective spaces or spatial structures in general, topological spaces, manifold, etc. This is explicit in some research programs in geometry, like those of Klein and to some extent Riemann, and of course it is still in the air, let's say, in the last decades with William Thurston, for instance, work on hyperbolic geometry, which is also a general theory of spaces in some connection with the theory of groups, like a neo-Kleinian program or something in Grothendieck generalizations of the concept of space. However, what is important for us as historians is to understand well that geometry had not always been conceived as a science of space. Rather, if you look at classical geometry, at the foundations of classical geometry, the elements of Euclid, for instance, you will find no references at all to space, to place, to topos or chora or whatever in Greek may vehiculate the idea of space. And the same is true for a long tradition of studies in classical geometry. The same is true even for philosophical presentations of this geometry. That is, if you ask to Plato or Aristotle, that were more or less contemporaries of the content of Euclid's elements, you will find that they explicitly denied that mathematical objects, mathematical figures are somewhere or in space. That is, the conception that is vehiculated by these philosophies of mathematics and by the elements of Euclid and Greek geometry as a whole is that the object of study of geometry are the single individual figures. That is, it is a theory about triangles, about circles, about squares, but these figures are not conceived as embedded in a bigger space, and much less anyone suggested that such a background space could have geometrical properties. So this was the situation with Greek geometry, and this is the situation that we find also in Arabic geometry, in medieval Latin geometry, and in Renaissance geometry. So my question has been, what made geometry into a science of space? What was the idea behind of assuming space as the object of geometrical investigation? And I think this is an important question for the history of geometry, because when geometry became a science of space, everything changed in a sense in its content. For the first time, one could expect to explore different structures, different spaces, different geometries. There was not just the Euclidean geometry, but all the other many geometries that we are accustomed to nowadays. And of course, saying that geometry is the science of space has important consequences also on the general history of science, in the sense that it immediately opens towards the possibility of a geometrization of the world, in the sense that insofar as the physical world is in space, of course, one can say that geometry applies to the world itself. So the question was, when this transformation happened, and how, and why? And of course, there is no simple answer to these big questions. It is a process that took centuries and many people and many disciplines and many perspectives. I put some there. It was a development in pure mathematics, of course, but it was a development that took parts from the history of mechanics, the history of optics, the theory of perspective, where places and spaces were mathematized in order to represent things in some ways. In astronomy, in cosmology, in geography, and mathematical cartography, in natural philosophy, and of course also in philosophy and in metaphysics. It is not strange, though, that we find the first ideas of geometry as a science of space in the 16th century. That is, at the wake, in fact, of the so-called scientific revolution of the early modern age. And as far as I understand, the first people who ever claimed that geometry is the science of space was, in fact, a philosopher called Francesco Patrizi, who is not very well known, but he was one of those philosophers living in the second half of the 16th century who challenged the Aristotelian scholastic philosophy, and did that by making strong use of a metaphysical notion of space. He's one of these people who said that space, conceived as a three-dimensional extension, infinite, preceding all the material things, is something that Aristotelian philosophy cannot account for. And so it is a new thing that shows that we have to change the Aristotelian philosophy and embrace something different. So he wrote this Discussiones Peripateticae against Aristotle, and then he wrote this important work, the Spatial Fisico et Mathematico, in 1587, in which he expounded his new conception of space. This was happening in the same years with other thinkers like Giordano Bruno and others that more or less in the same years were following a similar program in philosophy. What is interesting, though, is that Francesco Patrizi is the only one among them to write also a book on geometry that he called Della Nuova Geometria. It is written in Italian, and then he translated it into English in his major philosophical work, De Nova de Universis Philosophia, that is a new philosophy about everything, something like that. And in this Della Nuova Geometria in 1587, Patrizi says that he's taking a royal road to geometry, which is entirely new and never attempted by any ancient or modern. And then he says that, you see here, all mathematical sciences are neither abstracted from natural things, this would be the Aristotelian position, nor are in the imagination, as some Neoplatonists said, nor in the intellect, as Plato himself said, but space is their subject. Lo spazio è generale lor subjetto. And I think that this is the first time that someone was so clear, so open on space as the object of geometrical investigation, and with an emphasis of saying, this is a new theory, this is a new geometry that I'm proposing. Unfortunately, Patrizi was another mathematician. So these statements come from the preface of the new geometry, but the content of the new geometry is, well, it's a kind of a disaster. It covers more or less the first half of the first book of the Elements of Euclid in like 200 pages, and yeah, you see here it is in 15 books, 238 theorems. He redemonstrated the first 32 propositions of book 1 of the Elements, and not even in a very good way, so that Leibniz, when he read Patrizi, he said, you see, in the beginning of the book of his new geometry, there is something interesting, that is this conception of a geometry of space, mais les dedans fait pitié. But the interior of the book, the thing itself is a, well, not very good. and he was right, of course. But the point of mentioning Leibniz here is that somehow he took the lead from these ideas of Patrizi, and he attempted to work out something like geometry of space. I may say something more, that is to say that Patrizi's idea that geometry is a geometry of space was generally accepted by a certain number of people in the 17th century. Patrizi was better known than today. And so this idea that geometry had something to do with space, thanks to all this previous development that I mentioned before, that is in optics, in mechanics, in the theory of perspective, etc. This idea was accepted by several people. However, it was not easy to understand what to do with this idea of a geometry of space. That is, many people just continued to do, in some sense, the standard Euclidean geometry, but just saying that the objects of geometry are parts of space. That is, that rather than considering a triangle in isolation as a kind of Platonic idea, you should consider that a triangle is a section of space, and therefore, for instance, you may apply geometry to the word, because the space is where triangles are. Many other people, of course, accepted in general Patrizi's and Bruno's and others' new metaphysics of space as a three-dimensional extension, but without consequences for geometry. So I will mention just here Newton. I don't think we know whether Newton read Patrizi in person or not. Possibly he came accustomed by of his idea through Henry Moore, through Gassendi and others that explicitly quote Patrizi when they expound their own ideas of space. But in general, you find in Newton some ideas about space as the substrate of geometrical objects, as you read in the De Gravitatione, in the sense that Well, you see all kinds of figures everywhere, spheres everywhere, circles everywhere, etc. So the idea is that space is a kind of repository of all geometrical shapes, all geometrical forms. And yet, geometry, even though it may be characterized in this sense as a science of space, because space is where geometrical figures are, geometry is still for Newton mostly an investigation of those shapes. That is, an investigation of the properties of a parabola, of a conic section in general, of a triangle. What is missing here is to see space itself as an object of geometrical investigation. That is, not the things in space, but let's say the shape of space as such. And this, I think, happened, in fact, for the first time with Leibniz, more or less in the same years of Newton, of course. Leibniz is famous nowadays among the historians of philosophy about space because he advanced a new theory of space, a new metaphysical theory of space. And because he contrasted, in fact, his own theory, which is called the Relationist theory or something like that, with Newton's own theory. And for Leibniz, space was just a system of relations, not anything substantial, not anything absolute, as Newton and Patrizi wanted, but rather just a system of relations between or among things. He expounded this new philosophy of space in a famous correspondence with Samuel Clarke in the very last year of his life, in 1715-16. Leibniz died in 16. The Leibniz-Clarke correspondence was published the year after by Clarke, and became a kind of best-selling book in philosophy, and so everyone discussed after that whether space was considered as a substance or rather as a system of relations. Now, this is very well known. What is less known is that this idea by Leibniz, well, I give you some quotes, I hold space to be something purely relative, just like time. I hold it to be an order of coexistences, as time is an order of successions. Space denotes, in terms of possibility, an order of things that can exist at the same time, considered as existing together without entering into their particular manner of existence. So I say that space is an order of situations, an order according which situations are disposed, and abstract space is that order of situations when they are conceived as being possible. So it is a very abstract notion of space as an order of relations. I may also add that this reduction that Leibniz did of space to an order of relations and to relations was seen as highly problematic at the time, even from a metaphysical point of view. Because, of course, Leibniz is saying here something like that space is an order of situation, then what is a situation? And a situation is for Leibniz a kind of spatial relation. But, of course, you cannot define spatial relation, space to spatial relation. So it seemed to many that space was, let's say, such a simple thing that you could not really define it. And if you attempted to define it as an order, a system of something else, you entered in some kind of circle, because an order of situation would be an order of spatial relations and nothing more. This is explicitly said by Newton, commenting the Leibniz-Clarke correspondence. We have a letter from Newton to Conti during the exchange, in which Newton criticized Leibniz, saying he, Leibniz, say that the space is the order of coexistences and time is the order of successive existences. I suppose he means that space is the order of coexistence in space and time the order of successive existence in time, or that space is space in space and time is time in time. And the same is repeated by Clarke in the correspondence. It seems to me that Leibniz definitions amounts to this, that situation is the cause of situation. So from a metaphysical point of view, there were difficulties that were raised by these people. What these people did not know, though, was that since many years, since many, many years, Leibniz had a program in geometry, not just a program in metaphysics. And this program in geometry consisted in developing a geometrical theory of situation, which we call today the analysis situs of Leibniz. The analysis of situation. The analysis of situation, the analysis situs of Leibniz remained unpublished. So Newton and Clarke could not know anything about that. And in the following centuries, it was a kind of a dream for mathematicians. That is, Euler, Grassmann, Klein, Poincaré, all referred to Leibniz's lost analysis of situations as very different mathematical endeavors. That is, Grassmann took it to be vectorial calculus. Klein thought it was projective geometry. Poincaré thought it was topology. It was neither of these things, in fact, none of these things, but was nonetheless a kind of reworking of elementary geometry, metrical Euclidean elementary geometry, so nothing so fancy, through the notion of situations and relations. So, for instance, he defines the relation of situation. What he says, just like Newton said before, I cannot really define what a situation is, but I can define what does it mean to have the same situation. In doing this, I'm doing like Euclid, who never defines what a ratio between magnitude is, but what a proportion is, that is, what is the equality between ratios. So in the same sense, I can say that points have the same situations among them to another group of points if they are congruent to one another. So for instance, point A, B, C have some relations of situations among them, let's say the dotted lines in some sense, and this relation of situations are the same of those entertained by A prime, B prime, and C prime, because these two groups of points are congruent to one another. So in this way, you see that the situational relations is a kind of, I mean, in modern terms, it is not actually a distance, but it is something similar to a distance between 2 points. From here, he produced many hundreds of pages of attempts of articulating a geometry on this basic notion. But what is most important for us is that he held this conception of space as a system of situational relations. So if you take this in a more general way, this means that Leibniz's conception of space as a system of situation is a system, let's say, of the distances of all points among them, or something like that. So it is something which is very similar to our notion of a metric space conceived as a structure. But what is especially important for us from the conceptual point of view is that just like a triangle or a parabola is for Leibniz a system of situational relations, so space as a whole also is. And so Leibniz's idea is that space as a whole has geometrical properties, just as any subspace of it as a smaller system of relations. And so Leibniz, for the first time, in fact, I think, in these papers, gives definitions of some properties that he called the uniformity, homogeneity, the continuity, the dimensionality, and what we call today flatness, not just of figures, but of space itself. That is, what does it mean for space to be uniform? What does it mean that space as a whole is uniform from a geometrical point of view, not just from a philosophical, general, metaphysical point of view, but what is the geometrical property that space must have in order to be uniform or homogeneous or continuous? And so he began a kind of investigation of spatial structures as such. He is not going much further. Of course, he is working all alone in Hanover. He doesn't manage to get collaborators on that, and he didn't publish anything. So what we find in his papers are definitions, first theorems, but not, of course, anything that can be compared with, I don't know, Gauss or Riemann Nachlass. Still, it is, I think, the main conceptual step forward has been made, and the following history of geometry and epistemology of geometry is in fact intertwined with the history of Leibniz manuscripts and Leibniz ideas, because even though the papers on the analysis situs were not published, he wrote to many correspondents on his new analysis situs. And so people knew that he was projecting something like a geometry of space. And so in the 18th century and then in the 19th century, this idea of a geometry of space was in fact developed by the same people that I mentioned before, Euler or Grassmann or Gauss or Riemann, etc., who referred to Leibniz continuously and took over a research program in geometry of which they didn't know anything or almost anything, but they did know that had to do with doing a geometry of space and treating space as a structure, as a system of relations of some kind. So the question that we may pose now to archival research is, I mean, why Leibniz did this kind of things? Why he decided to take this way of studying geometry, and when did it happen? This is also a very difficult question. I will not give you a complete answer, but yet, can we say more about, let's say, the moment in Leibniz intellectual development in which he arrived to this conception? And I think that thanks to his manuscripts, now we can. And this is the second part of the talk. So let me say something about the manuscripts. As I said, all of Leibniz's manuscripts on the analysis situs were not published by him. So they are kept now in Hanover, in the archive. And the Academy edition of Leibniz's complete works is now arriving to finally publish them. So let me say something about the Academy edition. It is an edition divided in several series by topic. Series 7 is about Leibniz's mathematical writing. It was started at the beginning of the 20th century, but did not proceed until in 76, Eberhard Knobloch took the lead of the edition of the mathematical writings and began to work again at the publication of all writings of Leibniz on mathematics. Up to now, from 76 to now, So in 50 years, more or less, 8 volumes have been published, covering, going in chronological order and covering Leibniz writing up to 1676, so when Leibniz was 30-year-old. So it is just really a beginning. And 22 more volumes are foreseen, and 50 years to make 8, 22, I don't know, but whether we will be able to be faster or not, but it will take a while. The next 3 volumes, so Series 7, Volume 9, 10, and 11, will be entirely devoted to geometry, thus containing all of Leibniz's work on analysis situs. So to give you an idea, they deal with 330 different texts divided in 540 sheets. They will be like 2,500 or 3,000 pages in print. 1/3 of these have been published by the 19th century edition of Gerhardt and the 20th century edition of Couturat and Echeverria, and some other papers have been published by me in the past. These 3 volumes will be divided into foundations of geometry from 77 to 87, from 88 to 16, and the collection of Miscellanea. The date in which they are expected are those, but I wouldn't count too much on them. And we are aided very much by a project that we have in Paris, and which is led by David Rabouin, of which he will talk in the afternoon. So there is now a collaboration between Paris and Hanover. So the volume in which we are interested now is, of course, the first, which is currently in some advanced state of production, and it covers what Leibniz was doing in geometry, basically in the 1680s. It is a very composite volume because these are very fragmented studies. Many papers are just one sheet with some notes, so it is almost impossible to date with exactness. And there are a lot of difficulties in organizing this material into anything consistent from the thematical point of view, or reasonable from the chronological point of view. So it's a tough work. However, I would insist today on the fact that what we find in these papers from the 1680s is right the genesis of the relational theory of space, and so the genesis of this idea that space itself may be the object of geometry. So for this reason, this is a very important collection of papers. And this is something that was not very well known. That is, that there are no traces of Leibniz theory of space as a system of relations before the late 1680s. This is not well known by Leibniz scholars because, in fact, the power of the Leibniz-Clarke correspondence was so strong on the conception of Leibniz in the literature that practically all the historians of philosophy have always believed that Leibniz had been a relationist about space throughout his life, because this was Leibniz's position as against Newton's position, working for, through models, let's say, rather than proper chronological and historical study. but we know now, reading these papers, that in fact, up to the 1680s, Leibniz was not a relationist at all. I mean, his geometrical writings do not have traces of space as a system of relations, and his philosophical writings neither do that. So if you want to go a bit into the details, we can say that from a metaphysical point of view, Leibniz endorsed the idea that space was something substantial, just like Newton, up to 1672, which are more or less, which may be more or less the years of Newton's De Gravitatione. So they were working, let's say, at the same research program in the metaphysical space. Then he abandoned this idea around 72, but it is all only by the late 80s that he embraced a new theory. I will be very quick here and will skip much of the things, but so here you have some declaration about the substantiality of space of Leibniz as a young scholar. Space is the first extended thing. Space is almost more substantial than body. So these are classical Newtonian or things that come from Patrizi, let's say. Then you have this kind of middle period in which space was for him something like an imaginary extension, but there are no references to relations as well. When Leibniz characterized space in the late 70s or in the early 80s, he called it a phenomenon like many other things in his philosophy. And then you find, finally, one paper from the late 1680s, which is called Specimen Inventorum. And it is in this paper that you have a marginal note in which Leibniz, for the first time, makes this astonishing remark. Space and times are not things, but real relations. There is no absolute space or movement, since there are no principles for determining the subject of movement. So here, space and times are called relations. And this is something that had not occurred before. We know that this is the first paper in which this appears, also because we have some papers that are clearly written just after that, in which he takes this marginal notes written on the Specimen Inventorum and develop it from a metaphysical, philosophical point of view. And then the geometrical paper arrives on working on what does it mean for geometry that space and time are nothing but relations. So we can refine a bit the question and say what was Leibniz thinking when he was writing the Specimen Inventorum, and when did it happen? Now, this is a difficult text. It was published for the first time by Gerhardt in 1890 without the marginal notes, because Gerhardt found, well, this is a question of how to do critical edition of writings. Gerhardt believed, rightly so, that the marginal notes had no connection with the text itself, and so he didn't publish it. So what we can do, what we can think, is that Leibniz, as a matter of fact, had this sheet of papers on which he was writing the Specimen Inventorum. Then he went distracted by something else, we know what, and he wrote, well, remember, space and time have relations there. Since there is no connection, Gerhardt didn't publish it, and so scholars didn't know about this thing. Many, well, almost all the French and German and English edition of Leibniz papers are based on Gerhardt edition. So also the modern translations just missed this marginal note. An English scholar, Harry Parkinson, in 74, published for the first time a kind of critical edition of the Specimen Inventorum with the missing note. So for the first time, one could read it in Latin in the critical edition by Parkinson, this note. And Parkinson dated the essay to 1686 because it was similar to some of Leibniz papers from that year. So another literature said, yes, this is from 1686. However, again, some progress of the Academy edition, we can look at the paper of Leibniz, Specimen Inventorum, and see that the watermarks on the paper come from an Austrian paper from Vienna papers. So here is the manuscript of the Specimen Inventorum. Here is the famous marginal notes in which Leibniz for the first time says that space is a system of relations. If you look at this paper against the light, you can see two watermarks in the paper, and when you magnify it, you can recognize shapes, and going at looking at the archives, you'll find that this kind of watermarks only appear in papers from Austria, from Vienna. And we know that Leibniz was in Vienna in 1688. So we have a good way of dating this kind of paper. It is particularly helpful in this case that Leibniz moved from Vienna to Rome shortly thereafter, and this development that I mentioned before, in which he penned again down what space as an order of relations is, are actually on Italian paper. So we are pretty sure that not only he acquired the paper in which he wrote the Specimen Inventorum in Vienna, but that he used it in Vienna because after that he was using Italian paper. So the dating is I mean, not 100% sure, but quite reasonably that one. Now, what was doing Leibniz in Vienna in 1688? So we can try to understand what he was doing. But what he was doing a lot of things that he wanted to present to the emperor of the Austrian Empire, a lot of projects. But at some point, in the fall of 1688, something happened. That is to say, Leibniz received his copy of Newton's Principia that had been published the previous year. And so now we see something that we were not able to see before. That is to say that with this new dating of 1688 rather than 1686, we see that Leibniz was involved in something remarkable, that is reading the Principia. As a matter of fact, we even see that the watermarks on Leibniz's own notes on the Principia are made on the same sheet of paper, that is on the same kind of paper of the Specimen Inventorum. So what I was saying before, that Leibniz was writing and then was distracted, we can imagine that, as a matter of fact, Leibniz was reading Newton's Scholium, and at some point he decided that he had to go against this idea of space as an absolute thing that he found in Newton. He said, well, if space is not that, what is then? And then he wrote on a philosophical paper that he had at hand, the Specimen Inventorum, the space and time are not things but real relations. And you see there is even some references there, because Newton writes, there are therefore absolute places absoluta loca, and here he says locus absolutus, and then there are no principles for determining the object of movement is, of course, the point that Newton is making in the Scholium. And for instance, we know that locus absolutus is a term that never recurs again in Leibniz. So if he was writing it, it was probably because he was reading it somewhere. Even more, when we arrived at this definition of space as an order of situations, we find that this idea was in Newton. That is, in Newton's Scholium, he said, all things are placed in time with reference to the order of succession, and in space with the reference of the order of situations. This is Newton. And Leibniz was saying, well, so let's say that space is an order of situation, period. There is not true that things are placed in spaces, the order of situations, but that this order is everything we need to do physics. So if this is true, even Leibniz's famous definition of space as an order of situation is taken from Newton. I mean, not in the sense that Newton believed that space is an order of situations, but in the sense that the expression appears in Newton's Scholium, and Leibniz is taking this expression from there. We may add another further development about the importance of critical additions, because I mentioned before that Leibniz, before arriving to this idea, had characterized the space as a phenomenon. And after 1688, he never did this again, because an order of things is not a phenomenon. Now, this is a problem in Leibniz literature, because, of course, without knowing all this story, there are people who says, well, maybe Leibniz, once he says that space is a phenomenon, has another meaning of phenomenon, because they do not know, they do not think that there is an evolution in Leibniz thinking. So they take phenomenon to mean somehow an order of situations, but this doesn't work. Now, we know, looking at the following papers, what happened. That is, that Leibniz abandoned the idea that space is a phenomenon. So Leibniz wrote to Arnaud in October 87, matter considered as mass itself is only a pure phenomenon or well-founded appearance, as also are space and time. So October 87, space is a phenomenon. Then you have the Specimen Inventorum, in which he says that space is just a relation. And then on that Italian paper that I mentioned before, in spring 89, Leibniz wrote again a treatise on metaphysics that he called Prima Veritates, the first truths. And he wrote at some point what space is. And he writes, space, time, extension, motion are not things but fait. And he stopped. And belated it and said, way of considering things. So this, I think, marks the very moment in which Leibniz realized that space and time conceived as orders and relations cannot be phenomena at all. In fact, he was not very happy with this modi considerandi, and then he deleted again everything and said extension, motion, and bodies are not substances but true phenomena, and space and time have just disappeared in the freer copy. So you see that in order to understand that, you need to have a critical edition which contains also the erasures of what Leibniz first wrote and then deleted when he changed his mind. In any edition like the Gerhardt edition or any 19th century or early 20th century edition, this could not be detected at all. So this is something that you have to look at the Leibniz edition of the Academy, look at the notes in which they do write, actually, they do provide all the erasures of Leibniz. This is particularly difficult because it is a kind of double erasure. So it is difficult to signal, and I mean, at that point, you'll be better to look at the manuscript itself. But still, you have an indication, and this is precious. So to conclude, what I'm saying is that looking at these papers from the 1680s, we have discovered something that we didn't know before. That is to say that Leibniz's very famous theory of space as a system of relations that he opposed to Newton and Clarke in the last period of his life was not conceived without any interest or reference to Newton and then clashed with it. Rather, it was conceived from the beginning as an answer and a reply to what Newton had done in the Principia Mathematica. So Leibniz realized that Newton's Principia were an outstanding work of science, and first of all, he thought, how can I destroy it in some way? And he thought, well, the theory of space is where I can go to leverage something against Newton. And he wrote, space is not a substance, but rather a system of relations. But then you have a kind of important heterogenesis of ends, in the sense that Leibniz replies to Newton from a metaphysical and physical point of view, well, I wouldn't say weak, but of course controversial. That is, no one would espouse now Leibniz's position in the Leibniz-Clarke correspondence. We know that Newton had very good reasons, of course, to oppose to what Leibniz was saying in the Leibniz-Clarke correspondence. And yet, what Leibniz produced by discussing Newton and going against Newton was a new way of looking at geometry. Because he conceived at that point space as a system of relations. He had his own geometrical program on the analysis situs and began to work to a new geometry of space conceived as a structure and a system of relations. And this idea remained in the history of mathematics as a very important and strong idea towards structuralism, towards, let's say, non-Euclidean space and non-Euclidean geometry, Riemannian manifold, and everything. So it was the beginning of something new, not in the history of mathematics, and not only in the history of mathematics and physics, but of metaphysics and physics, but especially in the history of geometry. So I will stop here. Thank you.
Thank you very much, Vincenzo. A very rich presentation. We have time for questions. 1 and 2.
So thank you. That was super interesting. And I wanted to ask about the reception history of this text, because you had said that like Grossman and Klein and Poincaré all had their like interpretations.
Sorry.
You mentioned that like Grossman and Klein and Poincaré all had their interpretations, and you also said like, there was this prefigured metric spaces. But the thing it really made me think of was like Hilbert's Foundations of Geometry. Do you know what this made me think of was Hilbert's Foundations of Geometry? Yeah. Because, like, in particular, right, there is no, like, notion of metric here. He is actually thinking out space as relational, and then what Hilbert does is he actually proves that you can have this unique model that, like, Leibniz desired. And so I was wondering, was Hilbert reading this when he was coming up with that? Or was he not familiar with it?
We do not know much about Hilbert himself. That is, Hilbert's sources are mostly Pasch and other late 19th century geometers, and Pasch, for instance, mentions Leibniz works on the analysis situs, and Scholium. That is, there are German mathematicians in the second half of the 19th century who mentions and develop a bit of Leibniz analysis situs. So I do not think that Hilbert, neither in the Grundlagen nor in the lectures that brought to the Grundlagen that now we have ever mentioned Leibniz analysis situs. In a sense, he was taking a kind of different approach because in the Grundlagen he is working actually on figures, let's say so, and then he knows, of course, that space is the model there, but he uses it just like a model rather than as the system of geometry itself. So it is a complex relation, but I think it is an indirect influence in that case.
Okay, thank you.
Karine?
Yeah. Do you think that space could be thought of in the plural for Leibniz, and if not, what does it tell us about what his space was?
Okay. Well, this is difficult. In fact, it is very important. When he produces all these, when he defines for the first time all these properties like homogeneity, uniformity, continuity, etc., he applies them to some figures in space and says, for instance, that I don't know, a cylinder is uniform, the surface of a cone is not uniform, but it is homogeneous. That is, depending of his definitions, he gave different characterizations with these properties of different figures. And then he says, space is uniform, space is homogeneous. And then what he wants to do is to prove that. That is, he would like to start from his definition of space as an order of situation and be able to prove that since space is an order of situation, then it is homogeneous. And so from a modern point of view would be something like that for a metric space there is just one possible model, which is false. And so he struggles with that. At the same time, for instance, he is able to recognize that the parallel postulate is actually expressing a property of space, something which was not clear at the time, because the parallel postulate was seen as a principle on straight lines, on converging straight lines, but not as a principle on space. But at the same time, Leibniz would like to prove the parallel postulate, and so he dedicated many attempts at proving the parallel postulate. So he had, on the one hand, this idea that space is a structure, and so in principle it could be different. But then he also had this idea that one can geometrically prove what actual space is in a kind of, I mean, it is called sometimes a kind of logicist program in geometry. That is, you start from the principle of contradiction, the definitions of the things, and then you prove everything that is true in geometry. This cannot be done, and part of the 18th century discussion of what Leibniz was attempting to do here was to disentangle Leibniz's conception of space as a system of relations and Leibniz's program in logic of proving everything about geometry, and to have these two things separate. That I think it is what happens, in fact, with Lobachevsky, Boyai, etc., when they discuss non-Euclidean spaces.
Well, with the time approaching 12:45 and lunch beckoning, I think I will adjourn proceedings there. But before I do, let's please thank Vincenzo again for his